Okay, picture this. July 2nd, 2025. You're an astrophysicist, you're looking at the data streaming in, and suddenly the universe throws up this massive question mark. Cosmic paradox, really.
Yeah, there's something else.
We're talking about an explosion way out there in deep space. But it didn't just flash and fade like they're supposed to. No, this thing, it lasted an entire day.
An entire day.
Unheard of. And then, this is the kicker, it started repeating itself. Just
Damn.
Impossible based on everything we thought we knew.
Right. It fundamentally breaks the model.
Welcome to the deep dive. Today we're digging into the sources, the observations, the frantic papers coming out about GRB 25072b. It's this event that's just so bizarre, it's forcing scientists everywhere to basically go back to the drawing board. This isn't just some tweak to a theory. We're talking about rewriting fundamental ideas about how stars die, how black holes form, the whole cosmic catastrophe picture.
And it's crucial to understand the scale first, to really get why this is such a big deal. A normal gamma ray burst, a GRB, these things are the most powerful explosions in the universe since the Big Bang.
Right. More energy in seconds than our sun outputs in its entire life.
Exactly. 10 billion years of the sun's energy packed into maybe a few seconds or minutes. Just immense power. And, well, for decades, we had a pretty solid handle on what caused them. Two main scenarios.
Okay, let's set the stage then. Before this rule breaker came along, what were those established rules? What were the two sort of textbook ways GRBs happen?
Yeah, so for a long time, it was pretty clear-cut. For the longer bursts, the ones lasting more than a couple of seconds, the prime suspect was a collapser.
A collapse, okay.
Catastrophic core collapse of a really, really massive star. Think 25 times the mass of our sun, maybe more. Its core runs out of fuel, gravity wins, boom, collapses into a black hole.
Okay, so massive star death equals long GRB. What about the second type?
The second scenario usually explains the shorter bursts, the ones under 2 seconds. That's the merger.
Two things smashing together.
Right, usually two neutron stars, these incredibly dense remnants of dead stars. Or maybe a neutron star and a black hole. They spiral into each other faster and faster, and then cataclysm.
And the key point in both those scenarios, the physics everyone agreed on, was the timing and, well, the finality of it all.
Absolutely. Finality is the word. It's brutally quick. The core collapses in like less than a second, or the merger happens almost instantaneously.
And that collapse or merger launches these incredibly powerful jets.
Exactly. Relativistic jets. Plasma and radiation screaming out at almost the speed of light, focused by magnetic fields. If one of those jets happens to be pointing our way, we see it as a GRB.
But the source itself
is obliterated. Completely destroyed, annihilated. Whether it's the star collapsing or the two objects merging, there's nothing left. There shouldn't be anything left to, do it again.
Okay, source gone, one-shot deal. That's the rule book. So, GRB 25072b comes along and just rips that page out. Let's break down why it's so weird. Anomaly number one, the duration.
Oh, the duration is just staggering.
Yeah.
Typical GRBs, even the long ones we measure in seconds, maybe a few minutes tops. This thing, it was active for a quantity to maybe 1,000 times longer than a typical long GRB.
1,000 times.
Yeah. And it gets weirder. NASA's Fermi satellite saw the main gamma ray show, which was already way too long. But then the Einstein probe.
That's the joint Chinese-European mission.
Right. It looks at softer X-rays, and it revealed this thing had actually been simmering, emitting X-rays for almost a full day before Fermi even saw the main gamma ray burst.
A whole day before.
A day-long lead-up, then the main event. The energy required to sustain something like that for so long, it's just, well, it's problematic. We don't have an easy explanation.
Okay, so a day-long explosion is already breaking the physics, but that's only half the story. Then came the repetition.
Yeah, this is where it goes from weird to, frankly, impossible under the old rules. Fermi didn't just see one long burst. Over several hours, it detected 3 distinct, separate high-energy bursts coming from the exact same spot on the sky.
3 times. But you just said the source should be gone after the first one.
Exactly. That's the fundamental crisis. The first explosion, especially one lasting that long, should have used up all the fuel, destroyed the engine. How is there anything left to power bursts 2 and 3? What mechanism could possibly survive?
The immediate reaction must have been disbelief, right? Maybe the data was wrong. Or maybe it was close by.
That was the first thought, definitely. A kind of astrophysical defense mechanism. If something is this energetic, this long-lasting, this repetitive, maybe it's not actually that powerful intrinsically. Maybe it just looks bright because it's like in our own backyard.
In the Milky Way.
Yeah. If it's in our galaxy, the energy requirements are much, much lower. Still weird, but maybe manageable. Otherwise, the numbers become astronomical almost literally.
So naturally, telescopes swung around to pinpoint the location. What did the big guns, like the very large telescope, the VLT, find?
They pointed the VLT, Hubble 2, right at the coordinates. And the result was, well, it wasn't good news for the nearby theory.
It wasn't close.
Not even remotely. It was definitively extragalactic, located in a faint, distant galaxy, billions of light years away, potentially.
Billions. Oh, wow. So if it's that far away and still looked that bright and lasted that long.
The implication is just mind-blowing. Its actual energy output, the isotropic energy, has to be maybe 100 to 1,000 times more energetic than even the most powerful GRBs we knew about before.
So it didn't just break the duration and repetition rules, it smashed the energy scale, too.
Completely. It means whatever engine is driving this thing, it's not just surviving, it's operating with some kind of sustained, hyper-efficient process we haven't even conceived of before.
Now, you mentioned we had a couple of scenarios before, but the sources we looked at suggest that even before this monster event, things were getting complicated. GRB physics was already showing cracks, like the boat.
Yes. GRB 2310DNA, the boat brightest of all time. That was really phase one of this current, let's call it, identity crisis for GRBs.
What made the boat so special, besides just being incredibly bright?
Well, its brightness was off the charts. It saturated detectors. But scientifically, the key thing was what Fermi saw within the burst. For the first time ever, they detected a clear, high-confidence emission line.
An emission line, like a chemical fingerprint.
Sort of, but for high-energy physics. It was a spike at a specific energy, 12 million electron volts. It lasted for about 40 seconds.
And why is 12 MeV6 significant?
That energy is a telltale sign of electron-positron annihilation, matter meeting antimatter. It meant we were looking directly into the heart of the jet, the annihilation engine itself. It confirmed the physics inside these jets was even more extreme than our models predicted.
Okay, so Bowie gives us a peek inside the engine, but then came the follow-up paradox, right? JWST looked at the aftermath.
Right. You'd expect the brightest burst ever to come from the most spectacular stellar explosion ever. A supernova that would blow the star to absolute smithereens.
Makes sense.
But JWST looked, and the supernova associated with the Bs was, well, pretty normal. Almost boringly ordinary, considering the GRB itself.
How does that work? A record-breaking burst, but a standard supernova.
It forces a rethink. It suggests the GRB jet and the overall star explosion, the supernova, might be more decoupled than we thought. Like, the star dies in a somewhat standard way, but somehow the central engine manages to funnel a ridiculous amount of energy into these incredibly narrow-focused jets, maybe following different rules for energy distribution.
Okay, so Bowie complicated the engine. Then came the Einstein probe, you mentioned it earlier. How did that add to the confusion?
Einstein probe was phase 2. Its strength is seeing softer X-rays, a lower energy range than Fermi. And it started finding this whole hidden population of events, things that weren't quite typical GRBs.
Like what?
Events that got classified as failed jets or dirty fireballs. Basically signs of a massive star collapsing, but maybe the jet didn't have enough oomph to punch cleanly out of the star, or it got choked with stellar material.
So not every collapse makes a clean GRB.
Exactly. It suggests there's a whole spectrum of outcomes, from successful, bright GRBs to these choked jets, to maybe just a collapse straight into a black hole with no burst at all. The simple short-long classification was starting to look way too simple.
And there was one more just before, 25702b, right? GRB 2303078.
Yeah, March 2023. That one looked like it should have been a short burst, probably a neutron-star merger based on other properties. But it lasted much longer than the typical 2-second cutoff for short bursts. It blurred those lines even further. It seemed to have features of both merger-driven burst and collapse-driven bursts.
And that event also tied into the whole cosmic factories idea.
Precisely. JWST observed the aftermath of 230307 as well, and it found heavy elements like tellurium. It was more strong evidence that these violent events, even the weird ones, are where the universe forges elements heavier than iron, like gold, platinum, and, well, tellurium.
Okay, so the picture was already getting messy. The universe wasn't fitting neatly into the boxes anymore, and then boom, GRB 250702b arrives demanding completely new boxes.
Or maybe throwing the boxes out altogether.
So what are the leading ideas? The really exotic theories trying to explain how you get a day-long repeating burst from billions of light years away.
Well, they're definitely out there compared to standard models. The first one involves rethinking the collapse itself. Sustained stellar collapse.
Meaning the star just collapses really slowly?
Sort of. It proposes that this particular massive star didn't just collapse in milliseconds like usual, Somehow, its death throes were drawn out over an entire day, continuously feeding those jets.
But what physically stops gravity from just winning instantly?
That's the million-dollar question. Maybe extreme rotation. Maybe incredibly powerful, complex magnetic fields that somehow regulate the inflow of material onto the forming black hole, preventing it from swallowing everything at once and choking itself on. But yeah, it requires a major revision of core collapse physics.
Okay, so theory one is a super slow motion collapse. What's the next contender? This one seems to focus more on the repeating part.
Right. Theory two is unstable black hole formation. The idea here is that the initial collapse does form a black hole fairly quickly, but maybe it's not a clean process.
How so?
Instead of swallowing all the surrounding star material immediately, maybe the newly formed black hole is messy. It doesn't capture everything at once. Material swirls around it in a chaotic, unstable disk.
And then clumps of this material fall in later.
Exactly. You get repeated accretion events. Chunks of leftover stellar debris spiral back in, fall onto the black hole hours later, and each time one falls in, bang, it powers another burst. That could explain the 3 distinct peaks Fermi saw.
That makes a certain kind of sense for the repetition. But then there's the third idea, which sounds maybe the most mysterious, involving an intermediate mass black hole, an IMBH.
Ah, yes. IMBHs. These are sort of the awkward teenagers of the black hole world.
What's that?
Well, we know about stellar mass black holes, up to maybe 100 times the sun's mass, formed from single stars. And we know about the supermassive ones in galaxy centers, millions or billions of solar masses. IMBHs are predicted to fill the gap, maybe 100 to 100,000 solar masses.
But they're hard to find.
Very. They're kind of the missing link. We have candidates, but finding definitive proof is tough because they aren't usually gobbling up gas like their supermassive cousins.
So how does one of these theoretical IMBHs cause a GRB? I thought GRBs were from collapses or mergers.
This theory flips the script. It's not the black hole forming, it's the black hole eating. Specifically, an IMBH tearing apart a regular star that gets too close. It's called a tidal disruption event, or TDE.
Like shredding the star.
Exactly.
Yeah.
The tidal forces, the difference in gravity across the star, just rip it apart into long streams of
Hey, wait, standard TDEs, they're bright, but usually in X-rays, not gamma rays, right? And they tend to be one long flare that fades slowly, not repeating bursts.
Precisely. That's why this has to be an exotic TDE scenario.
Yeah.
It requires not just an IMBH, but an IMBH interacting with a star in a very specific way. Maybe the star's unusual, maybe they're in a tight orbit.
And that leads to the repeating bursts.
The idea is the star gets shredded into a really complex, clumpy, maybe elliptical disk of debris around the IMBH. This disk doesn't feed the black hole smoothly. Instead, clumps of material fall in periodically. Each time a clump hits the accretion zone, whoosh, a jet fires off, creating a burst.
In the day-long duration.
That comes from the sheer timescale of the IMBH consuming the entire star tidally. That whole process can take days, weeks, even months. So it provides a long-lasting fuel source tapped into intermittently.
Wow. Okay, so you need this rare IMBH meeting a potentially unusual star in just the right configuration.
Yes, it requires lining up 2 very rare phenomena to explain this one absolutely unique event. It's a stretch, but the event itself is such a stretch.
It really paints a picture, doesn't it? A star being slowly devoured, burping out these immense gamma ray blasts. So clearly, GRB 250702b is this huge challenge. What's the scientific community doing right now?
It's all hands on deck. Every major telescope facility is trying to get time to look at the afterglow, the fading light from the explosion's location.
What are they looking for?
Signatures. Chemical fingerprints in the light using spectrographs like VLT's X-shooter, trying to see if the composition matches a massive star explosion or maybe the debris from a shredded star, looking for subtle movements with JWST in the infrared that might hint at the dynamics.
And gravitational waves, could they play a role?
People are definitely checking the gravitational wave detector data just in case there was some compact object interaction involved that we missed. It's a multi-messenger puzzle now.
And for us, for the listener, why does cracking this specific puzzle matter so much, beyond just, rewriting textbooks?
Because GRBs, thanks to their incredible brightness, are one of our best tools for probing the very early universe. They act like cosmic lighthouses.
Shining through the darkness.
Exactly. Their light travels billions of years to reach us, passing through gas clouds, early galaxies. By studying the GRB light and its afterglow, we learn about the conditions back then. When did the first stars form? How did the first galaxies get built up? How did heavy elements get spread through the cosmos? GRBs are crucial flashlights for that history.
And it seems like the sources we read really emphasize a key point here. The reason these things are getting weirder isn't necessarily that the universe suddenly changed. It's that our view of it changed.
That's absolutely critical. Our technology has just gotten so much better. Fermi, Swift, now the Einstein probe, JWST, the ground-based telescopes. We can see fainter details, different energy wavelengths, react faster.
So we're resolving the complexity that was always there.
Precisely. We're peeling back layers. The old simple picture of just short bursts and long bursts was maybe an artifact of our limited observational capabilities. Now we're seeing the true, messy, diverse reality of how stars die and how black holes interact. Physics isn't breaking. Our understanding is just catching up to its richness.
So, GRB 250702b. It's this loud, insistent reminder from the cosmos that even the most extreme events we thought we understood have secrets. It's forcing us to rethink stellar death from the ground up.
Yeah, it really is. And it leaves you wondering, doesn't it? If this one event, this repeating day-long explosion from billions of light years away, can make us fundamentally question decades of physics, what else is happening out there? What other kinds of mind-bending, high-energy cosmic events are going on right now that our current instruments are still completely missing? What's waiting just beyond our current sensitivity?